Well, hey there, this is Mrs. Sharp, and today we are going to talk about Learning Target 2.4, which is right here in your notes as well, 2.4. Basically, we're talking about some fundamental ideas regarding matter. So how it is classified, you can see here, how it can be identified, what it looks like at the submicroscopic level, and some pure substance classifications. So here we go. Let's talk about elements first. What is an element? Well, elements are substances that cannot be broken down any further by ordinary chemical means. I suppose in there we could also add physical means as well, meaning changes. So can't be broken down by ordinary chemical or physical changes. That means in order to break down an element, you need to have a nuclear change. Elements are also considered pure substances, so we can go ahead and add that in there. A pure substance is something that is completely 100% uniform in the sample. So a sample of gold is going to contain 100% gold atoms, nothing else in it. Every single atom is going to be identical in terms of the number of protons it has, so it's uniform. So that's an element. Talked about those before, certainly. Some elements come in what's called a free or an elemental state, but most we don't find like that. Most are found in nature combined with other elements into compounds, which is another type of classification. So the fundamental units of elements, or the smallest piece you can get, smallest possible piece that is still an element. Those are atoms, and that should sound very familiar. There are 116 of those elements that have been recognized as official elements. Some periodic tables will show more or less, depending on how recently updated they've been. Of those 116, only 90 are naturally occurring. 26 have to be made by somebody in a lab. They don't occur in nature, so we call those synthetic. So there's our good old periodic table. Anything you find on the periodic table is going to be an element. So when you're asked if something is an element or a mixture or a compound, if you can find just that element by itself on the periodic table, then you will know that it's an element. Here are some types of elements. We have metals. Metals have luster, that means they're shiny. Fancy word for shiny there. They are good conductors of both heat and electricity. So it allows heat to pass through it. They allow electricity to pass through. They are ductile, meaning they can be pulled into a wire. They are malleable, which means they can be hammered into a thin sheet. And they're usually solids at room temperature, which means their melting points and boiling points are fairly high. And I think if you sort of conjure up a metal in your head, like let's say iron, that makes sense. It's a good conductor, it's ductile, malleable, usually a solid, or copper, very shiny, it's a good conductor. We use it for electrical wiring. Obviously we can pull it into a wire, and it's a solid at room temperature. So I think all that stuff is pretty much common sense. In addition to metals, we have non-metals. Oh, there's some metal forging happening. Non-metals are pretty much the opposite of metals. They are dull, they don't conduct very well. They're too brittle to be hammered into a thin sheet. They just kind of break into a bunch of pieces. Similar for a wire, they're not going to be able to be pulled into a wire. And they can be any phase, solid, liquids, or gases. Oh, there's some peanut brittle for brittle. And metalloids are sort of the junk drawer category. They really have properties of both at the same time, so we have a hard time distinguishing whether or not they're metals or non-metals. So we call them metalloids because they really act like both. Metalloids are awesome for things like computer chips and chips in your phones and stuff like that because of the fact that they can conduct, but not to a super high extent. They work really, really well for electronics. Here is a periodic table, and then you have this in your notes. And we're going to go ahead and distinguish our metals, nonmetals, and metalloids. So our first category is metals. If you look at this stair step here that sort of occurs between aluminum and boron, right here, all of these yellow elements are going to be considered metals. So metals are on the left-hand side of the stair step, and we use the stair step a lot to break up the periodic table. So these are all metals, all of this. Not hydrogen, which makes sense because we know hydrogen's a gas. And then these two rows down here as well. Nonmetals are anything on the right-hand side of the stair step. So you see we've got this sort of peach colored or salmon colored here over here. So much fewer, many fewer nonmetals. Remember, those can be solids, liquids, or gases at room temperature. And then we've got our metalloids, which are this mixture of both, which makes sense. It's got this yellow and salmon color. Those are your metalloids, so they fall right along the stair step. If they are touching the stair step, generally they're considered to be metalloids. So I would even say that that includes aluminum. So these are your metalloids, where they are actually bordered on one side by the stair step. So very few of those, right on the stair step, that dividing line. I want to go back here because I want to talk about these things called diatomic elements. Diatomic elements. Diatomic elements always need a buddy. So in other words, if you want some of nitrogen, for example, you will never find nitrogen written as N all by itself. It doesn't come that way. So it either needs to be in a compound with something else, like N2O. Well, here it's got a buddy. He's buddied up with oxygen, and actually there's two nitrogens, so he's got another nitrogen buddy. He could be just NCl, maybe, nitrogen chloride, so he's with a buddy. But if you want just nitrogen all alone, the element, he needs a buddy. So he's going to be N2. That's how we find nitrogen in the air. Never N, but N2. So these elements, when they're by themselves, they look like whatever the element is, X, and then 2 to show that they've got a buddy, two of them together. So your diatomic elements are these ones. I want you to know these diatomic elements. So we start with nitrogen, oxygen, and fluorine. All those are diatomics. Chlorine, bromine, and iodine. Those are all diatomics. And then our last one is hydrogen. So there are 7 of them. And they all need a buddy. So you'll never find them all by themselves. There's no such thing as chlorine all by itself. But you guys have heard of sodium chloride, so he's got a buddy there. There is, let's see, there's a lithium chloride. And if it's chlorine just by itself, it comes as Cl2 because he needs a buddy. So those are your diatomic elements. Oh, Mrs. Sharp loves Abby Kono. All right. Chemical symbols of elements. Let's talk about those. So chemical symbol would be something like gold. Gold's chemical symbol is Au. That's called its symbol. And those symbols are always based on the names, and the ancient ones come from their Latin names. So gold is an ancient element. The reason that it's so funky, AU, is because it's based on aurum, which is Latin for gold. Let's see. They are either 1, 2, or 3 letters long. So if you look at your periodic table, those symbols are either going to be 1 letter long, like W, that is tungsten. Lots of 2 ones, like HE for helium. Or 3, one of my favorites is unium, which unium stands for 111ium. That's so it's element 111. And you will notice that in those examples that I just showed you, the first letter is always capitalized, but the second and third never are. So let me just give you an example of why that's done real quick. If you have the element cobalt, its symbol is capital C, lowercase o. If you were to capitalize that, capital C, capital O is a compound of carbon and oxygen. So that's not an element because this second letter is capitalized, so that's just a new element. So it's carbon and oxygen. So it can get confusing if you don't remember that that second one always has to be lowercase. So this is carbon monoxide, by the way, which is totally different. Cobalt is a metal, it's shiny, it can conduct electricity. Carbon monoxide is toxic to humans. It's a gas at room temperature. It's odorless. It's certainly not shiny or metallic. So completely different things. So that's important to remember. Here's some old names. You don't really need to know these. I just thought they were interesting. We talked about gold. Silver has an older name, argentum, so that's AG. That's where it comes from. Cuprum is for copper, Cu, and lead comes from plumum, which lead was really used in the first plumbing pipe systems, and that is Pb. So a lot of them just make sense and are based on their names like we know them as, but some are a little bit older and therefore have these sort of older names for their... Okay, so let's continue on here. Here we go again. Oh, forgot iron and tin. They're funky too. Okay, let's transition into talking about compounds. We just talked about elements, now we have compounds. Compounds are homogeneous or uniform substances that can be broken down further by chemical means into 2 or more simpler substances. So, these are considered pure substances also because of the fact that they are uniform. And that's what this word homogeneous means, is uniform. So notice it says by chemical means. They cannot be broken down by physical means. So in other words, not physical changes. I can't break them down by melting them or grinding them into pieces or breaking them in half. I have to do some kind of a chemical change in order to break them down or to make them. So 2 or more substances combined together, they're homogeneous. The fundamental pieces of compounds are called either molecules or formula pieces. So remember, fundamental units are the smallest piece that I can get. And they can be molecules. That one should sound really familiar. Or formula units. Just be careful you don't abbreviate formula units FUs. That's bad. Compounds have formulas that never change. So if you were to write the formula for the compound water, that formula would be H2O. That formula never changes. That is the formula for water. If you were to change this formula, let's say it became H2O2, that's not water anymore. This is another compound. This is called hydrogen peroxide. So just by changing the formula, ever so slightly, it makes a completely different compound. And those formulas never ever change. The atoms in a compound are chemically bonded together. So that means they're stuck together. They're not just all floating around randomly. They're actually stuck together. So in water, back to our example, what you have is actually an oxygen that is stuck to a hydrogen and also another hydrogen. So they're actually stuck together. And water really does sort of look like this Mickey Mouse ears. And those three come as a package. That is one molecule of water. And in a compound, the original elements can't be recognized because a compound's physical and chemical properties are different than the original elements were. So for example, water is different than both hydrogen and oxygen. That's how it's made. I combine hydrogen and oxygen together, but I can't see any hydrogen or oxygen in there anymore. I've got a clear, colorless liquid here that is not combustible, whereas hydrogen and oxygen are both combustible gases. Now that I look at combustible, I'm not sure I spelled that right. It might be A-B-L-E. So the properties are completely different. It has changed into something entirely new. Here's an example that's really good too. Here I have some sodium metal. Sodium metal is silver. It is extremely reactive. And I have chlorine, which is this yellow toxic gas. And if I react those two together, those are elements, I am going to make sodium chloride, which is not poisonous, not reactive, something that we use every day to eat. So you can see how dramatically those properties are different. I don't see any sodium or toxic chlorine gas in there because this is a brand new substance. These properties are completely gone. And compounds are made from simpler substances by a chemical change. Again, they cannot be made by a physical change. I can't mix two things together, stir them up, and get a compound. They actually have to undergo a chemical change. Some examples of ways you can get a compound to be formed with a chemical change is by heating them, exposing them to light, or zapping them with electricity, or reacting them with something else. Elements and compounds are known as pure substances because their composition is constant. That means their composition never changes. Water is always H2O. Silver is always atoms of Ag. We know what their composition is, what they're made out of. What their makeup is never changes. Huh, that's what I just said. Oh, gold always contains atoms with only 79 protons. So let's contrast these with mixtures, which are two or more substances physically blended together. So these are physical changes making a mixture. So just mixing them up, not a chemical change. Think Chex mixture. There are no fundamental units, so I can't say they're made out of molecules or atoms. There just isn't any. The substances can be in any ratio, and the composition varies throughout, so there's no formulas to write. I can't write H2O because it could be H3O and still be the same mixture. That's not true for a compound. So because the composition varies throughout and there's no formulas, these are not pure substances. And because they're not pure substances, they're not called homogeneous. They are called heterogeneous. homogeneous, which just means non-uniform. So pure substances are exclusively elements and compounds. Substances in a mixture are not chemically combined. That means they're not bonded. Not bonded together. The properties of the original substance are retained. That means if I look at Chex Mix, I can see the individual pieces that I mixed together. Think about salt water. That is a mixture of salt and water, but it's still salty from the salt, and it still has properties of water too. It's just salty water. So I can still see properties of the salt, I can still see properties of the water, it's just all mixed together. And these can be prepared and separated by physical changes. Not chemical, physical. So here are some examples of ways I can prepare and separate these. I could filter it, set up a ring stand with a funnel and a filter paper and run it through. Some of the salad might stay here and the liquid would run through the filter. You could just evaporate the liquid. You could make a solution like the salt water. Mix it up. You could centrifuge it. That means spin it around really, really, really fast and all the heavy stuff falls down to the bottom. There's a centrifuge. That happens with your blood, by the way. Your blood is a mixture. It gets centrifuged in a lab and all the heavy cells go down to the bottom, and your serum, the liquidy part, stays on top, and then we can separate it. Distillation, which is when I take a liquid and I heat it up and turn it into a gas, and then I condense it back down. So I might separate two liquids that have a different boiling point. All examples of physical change. So there we go. That's the end of your 2.4 notes. Have a wonderful day.